Greetings. I want to talk about ramps today, and I want to think about what happens, what are the forces that act on an object that's on a ramp. And in this analysis, we're going to consider things we've been learning about forces and vectors, and we're going to put them all together. So first, imagine an object that's on a ramp, a block, typically. This is a standard problem you'll often see. And the angle of the ramp is this angle right here. That angle I'll call theta. And let's think about, first of all, what I really want to do is I want to determine what the acceleration is of the object on the ramp. That's kind of my primary purpose. Why else would I be doing this? One way you can think about this is, let's look at the extreme case. Let's make the ramp angle 0 degrees. If it were 0 degrees, the ramp would basically be flat surface right here. And there'd be my block. The acceleration in this case, hopefully you can see, would be that it would be 0 in this case because there's no force that's going to be pulling the ramp along. The other extreme case is this one, where the ramp is vertical. And you have the block here. And the angle is 90 degrees. In this case, the acceleration is going to be in that direction, and it's going to be equal to, you could say minus g, but I'm going to take the positive x direction to be in the direction of the ramp. So in this case, I would say the acceleration is equal to g. These are the extreme cases, and we're going to see if, hopefully they make sense to you based upon what you know already. And we're going to do an analysis with the ramps and see if we can get this result from our thinking. All right. Start off with a new page, and I'm going to redraw my ramp right here. And here's my object on the ramp. And I want to think about what forces are acting on the ramp, and on the object. So if I were in class, I'd ask you to name them. So maybe take a moment, pause the video, see if you can name them and draw them. One of them will be the force due to gravity. That'll be acting downward. You're always going to have that. Another one is going to be the normal force. But unlike the case with a flat surface, on a ramp like this, the normal force is going to be directed that way. Okay? Now, you might be tempted to say that there's some sort of a force acting in the direction of the ramp, this way. But I'm going to argue that that is a part of the gravity force. Some of gravity is going to be acting that way. So we're going to actually break gravity apart in a couple of minutes. But for the moment, the only two significant forces, or I should say primary forces that are acting on the ramp are gravity, downward, and the normal force at an angle perpendicular to the ramp. I'm going to draw a slightly bigger figure of the ramp right here. One thing that'll be useful in ramps is we're going to consider, and you'll see why perhaps in a minute, we're going to make our x direction be the direction of the ramp, because that's the direction in which the object's going to accelerate. So it makes sense that we call that x. The y direction, therefore, is always perpendicular to x, so it's going to be perpendicular to the ramp. This will make any analysis that we do involving forces much simpler. All right? So let's take a look at what's going on in both of these directions. In the x direction, let's think about what forces are acting on the ramp. In the x direction, I can see, well, the normal force is completely in the y direction, so I'm going to put y here, and I'll say, okay, that's all the normal force. But in the x direction, we have part of fg. I'll call it fgx. In other words, if this is my block here, I'll make it a lot bigger so I can really draw things. It's my object. This is my x direction here. What I'm arguing is part of my gravity is actually going to be acting along the ramp, and part of it is going to be acting perpendicular to the ramp. So I'm actually going to break gravity up into how much of it is acting in the x direction and how much of it is acting in this case, the negative y direction, because positive y is this way, and positive x is that way. All right, so that's what I'm interested in. And one of the things you can actually prove or can show is that this angle here, this is the angle of the ramp, this angle here has to be the same as that angle there, which you may look at that and have to think about it a bit, but it's actually true. And I'll just quickly show you why that's the case. This here is a right triangle. This here is a right triangle right there. And continuing on this angle comparison, this angle here is a right angle. That angle is a right angle. So these two are both right triangles, as I just mentioned. This line here and this line here are parallel because they're both downward. So that means that this angle there is the same as that angle there. And if in a triangle, if any two angles are the same, this one, and that one, and that one, then the third angle also has to be the same. So that shows you that this angle here, theta, has to be the same as that angle there. Now, why do I care? The reason I care is because this right triangle here that I'm circling will be the one I can break into the two components of gravity. So I have Fg, that's the weight of the object, don't forget. That's equal to mg. It's going to have an x component, which is in that direction, and it's going to have a y component that's perpendicular to the ramp. That's that way. And what I'm interested in, this is a right triangle. That angle there is theta. And if we know the ramp angle, therefore we know that angle theta. So using SOHCAHTOA, we could say that FGX divided by FG. FG is the hypotenuse. FGX is the opposite side. And FGY is the adjacent side. We know that FGX divided by FG is equal to the sine of the angle theta. So that tells me that FGX is equal to FG. Sorry, I'm off camera there. So that this FGX divided by FG is equal to sine theta. That tells me that FG, if I multiply both sides by FG, that FGX is equal to FG times sine theta. Multiply this by FG and multiply that by FG, and this is what you'll get. Remembering that FGX is equal to FG sine theta and FG is equal to mg, we come up with this equation that FGX is equal to m times g times sine theta. All right, I'm going to go back to looking at what forces are acting where. So in the x direction, right here, we said we have FGX acting, and that's the only force that's acting in the x direction. Here we go. All we have are FG and Fn. So in the x direction we have FGX, that's this guy. And in the y direction we have Fn and we have FGY. Those are the two acting in the y direction. So in the x direction we can apply Newton's second law. We can say F net in the x direction is equal to the mass times the acceleration in the x direction. In the y direction we can say that F net y equals, well, what's the acceleration in the y direction? We'll go back to this figure right here. In the y direction, which is this way, remember y is perpendicular to the ramp, is the object going to accelerate off the ramp that way? Is it going to accelerate into the ramp that way? Hopefully your answer to those questions is no. So F net y, therefore, is 0. So we can say F net y is equal to Fn, that's the force acting up, and minus FGY. That's equal to F net y, which is equal to 0 because there's no acceleration in the y direction. That tells me that Fn equals Fgy. And Fgx we came up with was Fg sine theta. So Fgy, and I'll redraw my triangle right here. Fg, Fgx, and Fgy. This is a right angle. So I have Fgy equals Fg cosine theta, and it's equal to mg cosine theta. That's what Fn is going to be equal to. Fn is no longer just equal to the weight, it's equal to the weight times cosine theta because it's on the angle of the ramp. In the x direction, remember all we have is Fgx. That's equal to F net in the x direction, which is equal to m times the x acceleration. And this is what I'm interested in. I'm interested in what is my acceleration in the x direction. So let's write what we know. We know Fgx is equal to Fg sine theta. That's Fgx. That's equal to max. Fg, don't forget, is equal to mg. So we have mg sine theta is equal to ma sub x. Cross out the m's, and we have a sub x equals g sine theta. So this is what the acceleration of a block down a ramp is going to be when there's no friction acting on the block. The only forces that we have acting here, as you can see in this original diagram I had, are gravity, which is this, and the normal force, which is that. And of course I broke up gravity into its x and its y components to do the analysis. But when I have that, and I place the block on the ramp, it's going to accelerate down the ramp with an acceleration of g sine theta. Now I'm going to take this back to the very beginning discussion I had with you. If the ramp is flat, make it flat, there we go. If it's flat, the angle's, if theta is 0 degrees, what's the acceleration that we came up with? We said the acceleration is 0. Well, what is the sine of 0? If I look at the equation here, the sine of 0 degrees is 0, so the acceleration, according to this equation, should be 0. Let's look at the other extreme case, where you have a vertical ramp like this, and you have your block on that ramp like that, and it's sliding down. The acceleration here, well, when the angle is 90 degrees, which is what you have when you have a vertical ramp, the sine of 90 degrees is 1. So the acceleration down the ramp is going to be g times the sine of 90, or g times 1, or just g. So when the ramp becomes vertical, has an angle of 90 degrees, its acceleration is going to be free fall, or at least downward g, because the direction of the ramp, remember, is what we consider positive. So we're taking the downward direction to be positive in this case. So the acceleration in this case, down the ramp, is going to be g. In general then, it's going to be g sine theta. We'll do a couple examples of that in the next video.